Hello, everyone. So today we're going to be continuing our conversation about the non-ideal behavior of thermodynamics by focusing a little bit more in on enthalpy. And this means that we're going to be bringing up something called the Joule-Thomson effect. So in order to try and describe the more general behavior of enthalpy, we're going to be starting from a very similar set of principles that we did from internal energy. Namely, that we know that enthalpy shows a dependence upon pressure and temperature. So then again, using calculus, we can split this dependence on pressure and temperature into possessing two different coefficients. One is going to describe the isothermal variance with pressure, and the second is going to show the isobaric variance of enthalpy with temperature. Now, in this case, we actually get kind of lucky because we've already talked a lot about the isobaric variance of enthalpy with temperature, because under isobaric conditions, this term drops to zero, and it turns out that then this makes it equal to heat. Woohoo! That's actually a really useful metric because, again, that means that this coefficient is the same as our isobaric heat capacity, which again, we've already shown. And then this gives us a lot of power because I've now solved half of this equation. Unfortunately, I still need to come up with a solution to describe the isothermal variance with pressure. So in this case, we're going to essentially pull out our old friend, the triple product rule. And then using the triple product rule, what we end up generating is the isothermal variance of enthalpy on pressure is going to be related to the isobaric variance of enthalpy on temperature, and essentially the isenthalpic variance of temperature with pressure. Now, it turns out we've already, again, described this first term because that's just our old friend, the heat capacity. Unfortunately, we've also done the classic PChem thing and kicked the can down the road because now I need to come up with a description of the change in temperature with pressure under isenthalpic conditions, which we're going to call the Joule-Thomson coefficient and give a variable of mu. So the Joule-Thomson coefficient, again, is a little bit weird to work with because it's essentially under isenthalpic conditions. And it's worth noting that some people will end up using the Joule-Thomson coefficient, but it's also often replaced with what's called the isothermal Joule-Thomson coefficient, or this mu t. So again, make sure you watch your subscript because mu t is going to be our general change of enthalpy with pressure over temperature. So to a certain extent, what we're really after. Whereas the Joule-Thomson coefficient without the subscript is relating temperature to pressure. So these are going to be related by negative Cp, but it does end up providing us a little bit of need to be very careful to watch your coefficients and make sure that you know when I say isothermal Joule-Thomson coefficient, this is going to be very different from our Joule-Thomson coefficient. Though again, they are related by a simple parameter. But one of the big advantages of these equations is that they are going to give us a more general description of enthalpy change. So again, using the Joule-Thomson coefficient, I can substitute that in, and we're going to find that enthalpy will change with pressure based on the heat capacity, the isobaric heat capacity, and the Joule-Thomson coefficient, and will vary with temperature just simply based on the isobaric heat capacity. So again, it is worth noting that unlike our internal energy, our heat capacity shows up twice in our more general equation. But again, if you want something to write a little bit more simply, this is where that isothermal Joule-Thomson coefficient pops in, as it helps simplify our general enthalpic equation. But again, we still have a slight problem because I need to find a way to measure my Joule-Thomson coefficient, at which point I get my isothermal Joule-Thomson coefficient as long as I have a good description of my substance. But in order to do that, I need to be able to look at isenthalpic systems. So I need a good way of talking about how temperature and pressure are going to vary with each other under this very important isenthalpic situation. So we need to go ahead and find a situation that might be isenthalpic, and then we're going to have to prove it to be able to make this temperature-pressure relationship. So in practice, what we often are able to do is measure our Joule-Thomson coefficient by letting a gas expand from a high constant pressure to a low constant pressure. So we're dropping our pressure, and then we're going to measure the temperature change. But we need to go ahead and prove that this is going to occur under isenthalpic situations. And again, one of the big advantages is, since enthalpy is a state function, all I need to show is that if I drop my pressure from a high pressure to a low pressure, and again, letting the volume and temperature vary naturally afterwards, that this is going to occur isenthalpically. And because I like my equations to be as simple as possible, we're going to be looking at a adiabatic scenario. So again, where we've got no heat transfer. So we're going to be looking at the scenario in essentially the most ideal situation, which is our good old friend, the piston. So we're going to be looking at pumping a gas at high pressure, isobarically, till I essentially force it into some sort of throttle, or essentially some sort of zero volume state. And then I go ahead and let it expand isobarically, again, against another piston. Now, it is worth noting that this is a scenario we're never going to be able to quite accomplish, but as long as our initial and final states are right, I still get to generate a path function, two path functions that I can add together to get my overall state difference and look at my enthalpy change from there. So we're going to essentially divide it into two work steps. The first of which is going to be the compression. And again, the work of this step is going to be our good old PV work, and isobaric conditions gets me one of the easiest variants of this equation, P delta V, no integration required. So in this case, my constant pressure is the same as my initial pressure, and my initial volume is, well, my initial volume. But my final volume is essentially zero as I pump down to the throttle. So in this case, I go ahead and let my signs cancel, and my work is going to be related to my initial pressure and volume. Then when I go ahead and let the system expand, my work is going to be, again, related to negative P delta V. In this case, I now have a final pressure of PF and a final volume of VF. But my initial volume was, again, that throttled zero volume. So now I have a work of negative PF VF. Now let's go ahead and use that adiabaticity. So my difference in internal energy is simply going to be the difference in between U2 and U1, or final minus initial, but that's also going to be the same as work plus heat from the first law. But we know under adiabatic conditions that Q equals 0. So I just have the work, which is just going to be work 1 plus work 2, or my initial pressure and volume minus my final pressure and volume. Now we're going to go ahead and rearrange this equation a little bit more to prove the isenthalpic conditions. And we're going to move all of our final conditions to one side. So I'm going to add PF-VF to both sides, and I'm going to add U1 to both sides to get my initial conditions all on one side and my final conditions all on the other. Now, this may seem a lot of work for nothing, but what it helps us prove is, turns out internal energy plus pressure and volume is the same thing as enthalpy. And same thing over here. So what we show is that my final enthalpy is the same as my initial enthalpy, which means my enthalpy change was 0. So this is actually kind of a cool idea, that as long as I've got isobaric an isobaric drop of pressure in an adiabatic chamber, I have an isenthalpic change of conditions. So now I just need to find a system that a real system that kind of models this sort of behavior. And it turns out that indeed we can hunt one of these down. And what we can do is, in practice, we're going to measure our Joule-Thomson coefficient by pumping in gas at a high pressure, and again, constant high pressure. So we're not going to let this pressure vary. And then we're going to essentially push it across a porous barrier, which essentially is going to allow us to create a pressure drop. So that the gas that flows out, it may be flowing out at a faster rate, but it's going to be flowing out at a much lower pressure. But again, what we can then do is measure the difference in temperature from this pressure drop. And by measuring the difference in pressure with this temperature, the temperature with this pressure drop, I know the change in pressure, I measure the change in temperature, and I get my Joule-Thomson coefficient. But let's go ahead and think about what we may end up observing. So if I have a temperature that decrease, well, I've got a pressure decrease, so negative change in pressure, and a negative change in temperature. So again, pressure drops, temperature drops. Then this, it gives me a positive Joule-Thomson coefficient. And here's going to be the real question of why does this happen? So this is going to happen under a situation where we've got attractive intermolecular forces. Because in order for the temperature to drop, I have to essentially have some form of loss of kinetic energy. And what I essentially did is I lost my translational energy, thus a decrease in temperature. This happened because I'm breaking apart my intermolecular forces, thus the decrease in pressure. Because remember, pressure is a good stand-in for concentration. So I diluted my sample and lost energy. So I moved my energy from my translational movement to break apart good intermolecular forces. And this is actually a fairly useful phenomena because it turns out it's really easy to heat substances, but it's often very hard to cool them. So if you have a substance with a positive Joule-Thomson coefficient, again, this has to be some sort of non-ideal gas, then guess what? You just created a refrigerator. So this is called a Linde refrigerator, and it's honestly one of the simplest forms of refrigerators that you can generate, because all you need is a porous barrier and essentially pumping gas through it. So it's a good, simple way to generate a simple refrigerator. But again, it entirely relies on the fact of the non-ideality of the gas that we're pumping through. In comparison, sometimes you're going to be pumping a gas through at high pressure, and you're going to see an increase in temperature. So negative change in pressure, positive change in temperature, thus a negative Joule-Thomson coefficient. And this negative Joule-Thomson coefficient is again representing an increase in temperature, and this is going to be due to repulsive intermolecular forces. So what I now have is a highly compact substance, which is essentially saying, I don't want to be with you, I don't want to be with you, I don't want to be with you, goes through the barrier, and I'm not with you, so I'm going to run away. And so I change that dislike of itself into translational energy, thus increased temperature. So again, this is entirely going to be due to intermolecular forces. So this is only going to be present for a non-ideal gas. And so what we find is if you have attractive IMFs, you're going to have a temperature drop, a positive Joule-Thomson coefficient. If you have a repulsive IMFs, you're going to have a negative Joule-Thomson coefficient. And if you're ideal and have no IMFs, then theoretically you should have a Joule-Thomson coefficient of 0, which again is one of the reasons why our typical ideal enthalpy equation is so relatively simple, because this term will go to 0 for an ideal gas. Now let's go ahead and try and look at this a little bit more on how our Joule-Thomson coefficient is going to be pressure, temperature, and identity of the gas dependent. So if I have, say, a relatively ideal gas, it's going to have a Joule-Thomson coefficient that's going to be, in general, fairly close to 0. But more importantly, let's go ahead and look at when it has a positive Joule-Thomson coefficient. So this is going to be the conditions at which the intermolecular forces are going to help keep the gas together. Well, it turns out helium only wants to stick to itself at very low pressures and very high temperatures. Because as soon as my pressure gets too high, I've essentially overcompressed the gas and it wants to expand. And if I heat it too high, then it essentially has more energy and it wants to go ahead and run around. But by the time we get to hydrogen, the intermolecular forces are much better. And so it's going to have a much larger region where the Joule-Thomson coefficient is, again, positive, attractive sort of IMFs. And then nitrogen, even more so. And we're going to be seeing a certain relationship in between the regions where we find positive and negative deviation, positive and negative Joule-Thomson coefficients, and the regions where we're going to be seeing deviations of our compressibility from 1. And again, this is the idea of non-ideality from a gas. So let's go ahead and look at hydrogen. And again, as a reminder, these all are looking at isothermal conditions, or at room temperature conditions. So a temperature somewhere around 300 degrees K. So under these conditions, hydrogen is almost always repulsive. So again, we see this by the fact that the Joule-Thomson coefficient is always less than 0. So again, repulsive conditions. And then for nitrogen, we see that we have to actually get to fairly decent pressures before we've driven our system to essentially being repulsive, or a Joule-Thomson coefficient less than 0. So again, we're going to see a lot of relationship in between our Z values and our Joule-Thomson coefficients. So again, under room temperature, we're going to find that a lot of gases are going to have a Z less than 0, at least initially, but you may see some systems where those repulsive forces dominate, and our Z will be greater than 1, and our Joule-Thomson coefficient will be less than 0. So again, we're going to be seeing a lot of these relationships. One of the other things to watch out for is a common metric of, again, this non-ideality, or where this attractive region is located at. And that's what's called the inversion temperature. So we see so any gas typically has 2 inversion temperatures. A lower inversion temperature. So this is a temperature below which the system is going to have a negative Joule-Thomson coefficient. So if I get too low in temperature, the system is essentially repulsive under those IMF conditions. But we're also going to have a upper inversion temperature, at which point the system now is going to be moving at such speeds is also going to be repulsive. And then in between these 2 inversion temperatures, this is where we're going to see this positive Joule-Thomson coefficient, where the IMFs are being relatively attractive. Now, we can go ahead and examine some of these for, say, low pressure or room pressure conditions. And under these conditions, we see actually quite a variety of upper inversion temperatures. Because again, we're not too often going to refer to lower inversion temperatures because they tend to be so low. We're more likely going to encounter the upper inversion temperatures. So for example, Helium has an upper inversion temperature of about 40 degrees, after which it's going to heat if I put it in a Linde refrigerator. Hydrogen has a value of about 202. Nitrogen is at 621. But by the time you get to, say, oxygen, we're at 794. Methane is way up here at about 1,000. And CO2, with even its still relatively minor attractive intermolecular forces, comes in at about 1,500. So again, this is a good kind of metric of how we can describe these Joule-Thomson effects. And again, once you have an idea of your Joule-Thomson coefficient, you can try and figure out which gases might be the most effective if you tried to, say, use them as an industrial coolant in a simple refrigerator. So this lecture, we've brought up some of these ideas of adiabaticity and how we might need to use this to, explain our Joule-Thomson effects. So we're going to be exploring adiabaticity a little bit more in detail next time. Till then, take care.